Hello, and welcome to the Computing Conversations column. This column is from the August 2013 issue of IEEE Computer and is titled Len Kleinrock, The Theory of Packets. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I'm the editor of the column, and I'm Charles Severance from the University of Michigan. In 1958, Len Kleinrock was wrapping up his master's in electrical engineering at MIT and preparing to start at Lincoln Labs when one of his professors, impressed with his work, insisted that he continue his education and pursue a PhD. Kleinrock decided that if he was going to invest the time, he would only work on an important problem, one whose solution would make a difference.
So I decided I'm going to work for the best professor I know at MIT, and that was Claude Shannon, the infamous, wonderful, magnificent person, Claude Shannon. So I called him up, and he invited me to his house, and we chatted a bit, decided, yes, we're going to work together. First thing I started working on, actually, was a chess playing program. Just working with the man was a delight. He was a great engineer, great mathematician, smart as heck, could solve a problem like that. And I looked around at my classmates, most of whom were working for him, and most of them were working on the kind of work he had developed, namely the field of information theory and coding theory. And I looked at them, and I had taken those courses, and I said, you know, the work that they're doing is the work that he left behind. Those problems that are left over are hard, and probably not of great significance, little bits and pieces left. I said, that's not what I signed up for. I wanted something to be fun, exciting, challenging, and have impact.
Researchers at MIT and Lincoln Labs were building computers that would ultimately need to talk to each other. Specifically, these computers would need to have interactions with many different computers that were short and bursty, followed by relatively long periods of no communication at all.
I figured the way to provide the communications would be to provide the ability for shared communication links. Because I knew that computers, when they talk, they don't talk the way I am now continuously. They go blast, and they're quiet for a while. A little while later, they suddenly come up and blast again. And you can't afford to dedicate a communications connection for something which is almost never talking. But when it wants to talk, it wants immediate access. So we had to not use the telephone network, which was designed for continuous talking, the circuit switch network, but something else.
Kleinrock took his inspiration from the techniques commonly used in the multi-user time-sharing operating systems of the time. If multiple jobs needed a large amount of processor time, you gave each job a short time slice, and when that time was up, you gave the processor another job for a time slice. This way, all jobs made some progress towards completion and evenly shared the delay due to oversubscription.
In time sharing, for example, which is the underlying technology that I adapted to communications, in time sharing, you want to let the little jobs go before the big jobs.
Yeah.
Because why should the little guy wait a long time for a big job? He's just going to get in and get out. So when jobs come in, you ask them, how long are you? And they're all going to say, I'm tiny. So you say, okay, you're tiny, I'll give you a little bit of time. And if you're tiny, you'll be out of there. No, I'll send you to the back of the queue and you get another tiny shot. The notion of round robin. So you get a little bit at a time, we're going to break you into little chunks. You get a chunk at a time. I said, that's a great idea for sharing communications. We'll give everybody a little bit of communications time. The little ones will filter out. The short jobs will filter out. When I say job, I mean message. A short message will filter out. And the long ones will take a little longer. And they don't mind being interrupted by the little guys. The important thing in this technology was not to make the very short messages wait behind very long messages. This automatic round robin, which is now called packet switching, you chop things into fixed lengths. You give them a little bit. If not, that's not enough. Give them another piece, and they go flying through the network on their own.
Kleinrock realized that when messages are broken into packets, and those packets are sent through the network using a round-robin scheduling approach, you could use queuing theory to build a solid model of the overall throughput and average message delay. It seemed simple enough, but as Kleinrock got into the details, it turned out to be challenging.
But getting back to what I said earlier, I set up this mathematical model. It was analytically intractable, and still is, by the way. I had two choices. One is give up and find something else, or two, make an assumption which allows them to move forward. So I introduced a mathematical assumption which cracked the problem wide open. From that point, I could just sail through the solution, get the performance behavior, get the design principles going forward. But then the question is, was that assumption any good?
What was the assumption?
The assumption was what I call the independence assumption, and it's absolutely a false assumption.
Oh.
It says when a message travels through the network, it changes its length independently every time it hits a new node on its hop through the network.
Right.
Mathematically, that creates an independence which allows you to proceed with the analysis. But it's clearly not true.
The real question, of course, was whether the simplifying assumptions skewed the theoretical results so that they wouldn't be useful as an approximation of real-world network behavior. Kleinrock addressed this by building simulation software that would test the independence assumption.
So what I had to do was to simulate a network with and without the assumption. I simulated many networks on a machine at Lincoln Laboratory, on the TX2 transistorized computer there. And I spent 4 months writing the simulation program without debugging a single line of it at a 2,500 line assembly language simulation. And I knew if I didn't get that simulation right, I would get no dissertation.
Right.
Ran it, tested with and without the assumption, and the results were amazingly close. So I had my solution. I could prove it would work. The package wouldn't fall on the floor. I could tell when things would work well and when they wouldn't.
With the mathematical model and the independence assumption validated, Kleinrock finished his PhD thesis in 1962. McGraw-Hill published it in 1964. The book was a clear roadmap as to how to build the scalable, shared, wired and wireless networks that we take for granted today. Its model was solid and its conclusions clear. All that was needed was to get to work and build the network.
Nobody cared. In fact, I went to AT&T, the biggest network at the time, and explained to them, you guys ought to give us good data communications. And their answer was, what are you talking about? The United States is a copper mine. It's full of telephone wires. Use that. And I said, no, you don't understand. It takes you 35 seconds to set up a call. You charge me a minimum of 3 minutes, and I want to send 100 milliseconds of data. And their answer was, little boy, go away. So little boy went away, and with others developed this technology which ate their lunch.
Right.
But nobody cared, and they said it wouldn't work. And even if it did work, they want nothing to do with it. So that was the environment we faced. It wasn't until years later, when the government decided they needed a network, that suddenly I saw a way in which I could implement the technology I had.
Finished with his PhD, Kleinrock prepared to begin his career as a Lincoln Labs researcher. It had supported him financially as he had earned his master's and PhD.
As I said, Lincoln Laboratory sent me for my master's dissertation. They also sent me for my PhD. So they supported me for years. Wonderful economic, financial, research environment support. And I felt an obligation to work for them. And I was prepared to take a job at Lincoln Laboratory, which is a great institution. And so when I went to work there, the first thing they said is, look, Len, why don't you look outside before you can commit to work here? Make sure there's nothing out there that you really would like better. This was a magnificent step on their part. So I took a trip to the West Coast. I went to some of the aerospace companies. I was not interested in university position at all.
Really?
But it turns out when I was going up to San Francisco to look at some of the high-tech companies up there, a friend of mine suggested I interview with Berkeley. So I did. I interviewed, I came back, they lost my case, they changed the chairman. I never heard from them.
Kleinrock was finishing at MIT when one of the professors at Berkeley who had met with him during the interview process came to MIT on sabbatical, and they ran into each other.
And he sees me in the hall and says, Kleinrock, how are you? And he thinks that I'm looking for an academic position. So he contacts one of his friends here at UCLA, who then invites me out here, offers me a job, and now I've got a dilemma. Do I want to teach? Do I want to cross the United States? It's almost like on a wagon train, 3,000 miles away from the East Coast where the world is, family is, for a job paying half that I could earn back at MIT Lincoln Labs, and try something that I've never tried before. So I went to the folks at Lincoln Lab, and I said, look, I've got this offer. It looks attractive. It's a new challenge. What should I do? And there was a wonderful answer they gave. They said, Len, try it. If you don't like it, come back. Wow, is right.
Yeah.
Well, I came here in August of '63, 50 years ago, and I'm still here.
In his 50 years at UCLA, Kleinrock has accomplished enough to fill several books. As the ARPANET project got off the ground, he founded the Network Measurement Center, and along with UCLA graduate students Vince Cerf, Steve Crocker, John Postel, and many others, was an essential part of the early ARPANET development. The first 2 packets ever sent across the ARPANET were sent from Kleinrock's lab at UCLA to a system at Stanford Research Institute. The network crashed after the second packet was sent. Beneath the millions of network links, billions of computers, and trillions of packets flying around the world at any given moment, a solid mathematical model developed back in the early 1960s proves that all those moving parts actually can work reliably. This column is from the August 2013 issue of IEEE Computer and is titled Len Kleinrock, The Theory of Packets. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I'm the editor of the column, and I'm Charles Severance from the University of Michigan.